So, good afternoon, students. So, again, kindly let me know if you all are able to listen and see me. So, good afternoon. And once you will confirm me that you are able to listen and see me, so we will proceed further. Okay, thank you, Vikla. So, I think I am audible to everyone and our setup is okay. So, basically in last classes we have introduced the concept of genetic structure of population, and today we will be doing our actual business, that is the estimation of the allelic and this genotypic frequencies. Okay. So basically, from today onwards, there are some simple derivations we will be taking up, through which we will be in a position to estimate the allelic and genotypic frequencies. And to be very frank enough, what I am going to teach you today and in coming classes, through my knowledge of statistics and in probability and other field, I am basically try to introduce the concept of dummy variable, through which it becomes very easier to estimate the allelic and genotypic frequencies in Hardy-Weinberg equilibrium as well as this genetic structure of population. So, how we do this? Okay, and the beauty of this method, which I am going to tell you, is that by using this method, it becomes very easier to make a generalization. Say, for example, here I will start from the single autosomal locus. You can move on to multiple autosomal locus and multiple alleles also. Okay. So that we will try to learn, because when I was studying in Falconer DS, the book we used to study, I was not able to find all these things. And thanks to the some of the new books, particularly from one of my favorite teacher, Dr. Bra, because he used to teach us when we were in Gadwasu. So there is a one book from Bra sir. So that also gave me a lot of motivation to do some more advancement and some more derivations that can be used for easing the calculation of all these genetic structure of population. So let us start today's lecture, and we will start from single autosomal locus. Okay, so autosome everybody know. So autosome is any chromosome that is not a sex chromosome, right? So we have a pair of sex chromosome, we have pair of different autosomes, right? So in genetics, what is locus? So one word is autosome. Now I have defined in first line that what autosome stands for. So any chromosome that is not a sex chromosome. And in genetics, a locus, for which the plural we used to say loci. Okay. So is a specific fixed position on a chromosome where a particular gene or genetic marker is located. So gene is nothing but it is the part of exome. Okay, that is the coding part of the chromosome or the DNA. Okay, so that particular span of that DNA that makes a definite biological protein that have a biological activity. So that particular gene is located at a particular place on the chromosome, and that is also known as genetic marker sometimes. Okay, so this loci stands for that place, that position where that gene is located, right? Now, genes may possess multiple variants known as alleles. Okay, this you know from the Mendelian genetics. And an allele may also be said to reside at a particular locus. Okay, so for a particular gene, there is a locus for two pair of chromosomes. So at one place, one allele may be there, or the contrasting character, that is the factor. Another allele may be located at the homologous pair of chromosomes at the same loci. Okay. Now, a gene is said to be polymorphic if more than one allele occupies that gene's locus within a population. So, what is when a gene is said to be polymorphic? That when your more than one allele occupies that gene locus within a population. In addition to having more than one allele at a specific locus, each allele must also occur in the population at the rate of at least 1% to generally to be considered as polymorphic. If you want to consider an allele to be or a gene to be polymorphic, so at least allele must also occur in a population at the rate of at least 1%. Okay, so if there are 100 people are there, a different form of allele must at least occur in at least in 1%. So that is the one of the requirement for a population to be called as polymorphic instead of monomorphic. There are in monomorphic there is only single this element, right? Now, so this gives us a cutoff, a mathematical cutoff to for a character to be called as a polymorphic or monomorphic, right? Now, however, what is important at a locus is the degree of polymorphism. And a locus in which there are 1000 equifrequent alleles would be considered more polymorphic than a locus which there are two alleles with frequencies 0.01 and 0.99. So they also told this thing, that is the degree of polymorphism. It is also important that is degree of polymorphism depends on the number of alleles rather than you have a single allele and how many people are having a particular allele or the other allele. So if a population is at a locus is made up of equifrequent alleles, say for example 100, 200, 1000, then that locus is said to be more polymorphic rather than locus where only two alleles are there with a frequency of 0.01 and 0.9, right? That is 0.01 means one individual in 100, 99 means 99 individual having another form of allele at a locus. So many authors now use the term mutation for any rare allele. So if in a population there is a difference in the this sequence occur due to mutation. Okay, na? So now many authors use the term mutation for any rare allele and the term polymorphism for any common allele. Okay, if there are more than alleles which are frequent, if there is a rare allele is there, then it is known to be a mutated form rather than a common allele. Okay, so now you must understand that what does a rare allele stands for and what is a common allele stands for, right? Now, let us consider some of the example under various modes of inheritance at a single polymorphic loci. So now we will try to understand under different modes of inheritance, okay, that how the genetic structure of the population will vary. Okay, so we will start from the two alleles. That is, we are having a gene and it is having the two form of alleles, right? Now, the genetic structure of a population under various modes of inheritance have been given below with the help of illustrations and examples. So, what are those illustrations and examples? So, first illustration I will be introducing to you is beta lactoglobulin in milk of cows. Okay, so let us have some background about this gene. So, the gene underlying the production of beta lactoglobulin protein in cow milk shows polymorphism, right? Which affects the amount of protein released. So higher level of beta lactoglobulin are associated with increased milk yield. So if you have higher beta lactoglobulin, so there will be increase in the milk yield and whey protein content. And low levels are associated with increased casein and fat content and are favorable for cheese production. So basically for commercial point of view, the amount of the beta lactoglobulin in the milk of cow is important, that whether they should be used for the cheese production or they should be used as a raw milk. Okay, so if so this low level and high level are associated, highly associated with this thing. Okay, Now we have two variants of the gene which are associated with the higher and lower level of the beta lactoglobulin in this milk. So say for example A is associated, A gene, that is the A form of the this allele, that is we are having two forms of the gene. One is A, other is B. So A is associated with higher relative content of beta lactoglobulin and B is associated with lower relative content of the beta lactoglobulin. And this particular gene is applicable to many breeds. And what will be your mode of inheritance? The mode of inheritance will be your incomplete dominance. So, because you have already studied all these mode of inheritance when you have studied this Mendelian inheritance, so I need not to revisit them. Now, simply I have said that it is incomplete dominance, so you know that what does I mean. So, what are the phenotypic effects? So, say for example, if at a loci, both the genes are capital A, the genotype will produce higher amounts of beta lactoglobulin, hence the higher milk production. If cow have A and B, will produce intermediate amount of beta lactoglobulin, and those of the cow with B and B genotype will produce low amount of beta lactoglobulin. Okay, so now let us do an example from this particular illustration, and then we will try to enumerate the genetic structure of the population based on the occurrence of these alleles in the population. Okay, so what is that example? 300 Holstein Friesian cows were tested for beta lactoglobulin gene polymorphism. And what is that gene polymorphism? That this SNPs, there is a conversion of G at 731 place, okay, where this guanine is this adenine is replaced by guanine. Okay, so if this guanine is there, so it becomes favorable for this beta lactoglobulin, and that is why this A and B type of alleles are formed. So in some of the alleles, that is in one form of the allele, at this particular point, if this locus, this G is present instead of A, and in B type, this A adenine is present instead of G. Okay. Now, so say for example, out of these 300, okay, so we have AA genotype 90 cows, AB genotype 150 cows, and BB genotype 60 cows. So calculate the gene and genotypic frequencies of this sample from the population. Okay. So now we have to calculate the gene and the genotypic frequencies, right? Now, since the mode of inheritance was incomplete dominance, right? The three genotypes can very well be differentiated phenotypically on the basis of beta lactoglobulin amount in the milk, right? So what that is how they have differentiated them. So they have milked them, and based on the concentration of the beta lactoglobulin, these can be differentiated. That 90 are of high level, then medium level is 150 and lower level is 60, right? So now, what is this method of this dummy variable? Okay, so what we will be doing, we will be making a table here. So this stands for the first allele, this stands for the second allele. Okay, now we know that because we are considering for all these genetic structure in the population, we are considering the diploid organism, and in a diploid organism you will also always be having two alleles at a time. That is, it is not like that an individual with a diploid organism can have this genotype AAB. It is not possible. Neither it can have ABB. So it can either have AA or AB or BB. Okay, these three can be the possibilities. So this will be shown by the dummy variables we will be using. So the dummy variable for one of the allele will be assigned randomly. Say for example, if I assign this 2, 1 and 0. So in the population, if I recall this as if this a random variable A, if I say A is a random variable, then the set of these will be 1, 0, 1 and 2, because it either it will be absent in an individual, or only one copy will be present, or the two copies will be present, isn't it? And why I am calling this as a dummy variable is, the reason is that once there are two copies of A are there, then it will automatically become 0. It is not random, it is assigned. That is, if two are there, then it will be 0. If it is 1, then the sum of the A plus B should be equal to 2. Okay, so if this is 1, then it will become 1. If this is 0, then it will automatically become 2, isn't it? So what will be the resulting genotypes will form? Okay, so the genotypes forms will be, for this it will be AA, for this it will be AB, and for this it will be BB. And now we know that what are the numbers n. For this it was 90, for this it was 150, and for this it was 60. So what you have to do is, you have to if I assign this by small n, okay, and this will be n dot dot, it will be equal to the sum of these, that is the 300. Okay, now how now we have to calculate the number of alleles. Say for example, these 90 individuals are having A and A allele, that is the two copies of the A allele. It means when we will be calculating about the, I am just removing this. Okay, so n into A. So what you have to do is, this value you have to multiply with the number of individuals. So it will be 2 into 90. Okay, it will be equal to 180, and this will be 1 into 150. So it will be equal to 150, and it will be 0 into 60 will be equal to 0. So it sums out to be your this NA, that is the number of alleles of A in the population. So now I am coming to the main thing. Okay, this will be 180 plus 150 will be 330. Similarly, you will do for this B, n into B. So it will be 0 into this 0 into 90, so it will be equal to 0. This 1 into 150, it will be 150, and this 2 into 60, it will be 120. So it total, this NB will be equal to 270. Right? Now, here what we need to understand from this table is that here two alleles A and B are two dummy variables that can take any dummy value among 0, 1 and 2, such that A plus B will always be equal to 2, since a diploid individual can have two alleles at a time. Okay, so this is what we need to understand from these two things. Now, the genotypic frequencies f dot 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 means here either A or B can come. Okay, is the relative frequency of that genotype in the genotype pool, and can alternatively be termed as the probability of occurrence of the particular genotype in the genotype pool. Say for example, if I say this probability of the occurrence of AA genotype, so what that will be? That will be equal to what are the numbers of AA individual in the population divided by total number of individuals with all the genotypes. Okay, so it is simply, this is your genotypic pool, isn't it? Because this is the total number of genotypes adds up. Okay, so these are the total number of genotypes available in the population, and this is your gene pool, that is total number of genes or the alleles available in the population. Okay, so basically when I want to find out that whether what is the frequency or the probability of occurrence of AA genotype, I have to divide this 90 by the total number of the genotypes available in the population. So it will be equal to 90 upon 300. So it comes out to be your 0.3. Okay, similarly for this second heterozygotes AB, it will be equal to number of heterozygotes divided by total number of individuals in the population. It will be 150 divided by 300 is equal to 0.5. And when we calculate for the genotypic frequency of the recessive, so it will be BB. So it will be number of individuals or the genotype, number of genotypes with BB genotype divided by total number of genotypes. So it will be equal to 60 that divided by 300. So it will be equal to 0.2. And we know from the probability, I told you people that when you will be coming for this class, you will just revisit the probability and the random variable chapter. So this is nothing but the relative frequency. And when you will adding up all these probabilities, so it is ought to be equal to 1. Okay. So when you will add all these probabilities, so it will constitute the exhaustive events. So it will equal to 0.3 plus 0.5 plus 0.2. It will always be equal to. Okay. So this is what I have told here. Thus the formula for calculating the genotypic frequency, if I generalize this formula, okay, in a diploid Mendelian population for a locus with two alleles can be generalized as, that is, if I do not define that what will be the first allele, what will be the second, it will be equal to n number of genotypes for that particular genotype divided by total number of genotypes in the population. So it will give you this formula. This formula will give you the genotypic frequency in the gene. Okay, and where this n is the summation of the n dot dot. That is, if I consider this as n dot dot, so if I sum all these up, so it will give you capital N dot dot. Okay, so is the sum of all the genotypes in the genotype pool, and n dot dot is the number of individuals with a particular genotype in the genotype pool. Okay, so this is how we calculate the genotypic frequency. Now, here we should note that if I add up all the frequencies, genotypic frequencies, it comes out to be 1. Okay. Second thing, probability of an event cannot be negative for any value of p. That is, it is always either equal to or greater than 0. And probabilities of all possible outcomes sums to be unity. And thus it qualifies that of the all the functions for a random variable. Okay. So it means these genotypes follows that random variable properties. Okay. Now we will try to find out. This is very easy, how to calculate the genotypic frequencies in the population. Now we will try to do the same thing for the allelic frequencies. Okay. So allelic frequencies. Now, from the table, sum total of all the alleles in the gene pool can be calculated as, in table if you see, so n dot dot was the total number of genotypes, n dot will be the total number of alleles, and it is nothing but the gene pool. Okay, so it will be equal to, that is, sigma of all these n dot. Okay, so here because there are only two alleles, so we will be adding them up, Na plus Nb, and that will be equal to 330 plus 270 is equal to 600. And one must note here that always this n dot is equal to twice of n dot dot. That is, the genotype pool, the number in the genotype pool, if you twice them, you will be getting the allele. Okay, let it be 3 alleles, 4 alleles, they all sum up to the twice of the this n dot dot. Okay, so here you might have seen that we were having the n dotted dot as 300. So if you multiply that by 2, that will be sum of this Na plus Nb. If there might have been 3 alleles, okay, then the sum of those 3 alleles will be twice of this n dot. It is always there. We will see in the forthcoming examples. Okay, so basically now we know that the total number of alleles in this population are 600. Now we have to find the allelic frequency, which can be denoted by f dot, and it is the relative frequency of that allele in the gene pool, and can alternatively be termed as the probability of occurrence of a particular allele in the gene pool. Say for example, I want to find out the probability of the first allele, then it will be nothing but the number of those alleles in the gene pool divided by total number of alleles. So it will be equal to 330 divided by 600. So it is equal to 0.55. Okay. Similarly, for the second also, you can find out number of that allele in the gene pool divided by total number of alleles in the population. So it will be equal to 270 divided by 600. So it will be 0.45. And again here also, if you sum up all the probabilities of all the alleles in a population, it will come out to be equal to 1. Okay, that is this plus this, it will be equal to 1. Right? Thus the formula for calculating this allelic frequency in a diploid Mendelian population for a locus with two alleles can be generalized as, okay. So here you can generalize them as this it should be actually not p dot dot, it should be p dot only, that is either a or b you will be putting here. So it will be equal to n dot divided by capital N. Okay, where this is the total number of alleles, and this is for a particular allele I am talking for small n dot. Okay, so this n dot will be sigma of n dot is the sum total of all the alleles in the gene pool, and n dot is the number of particular alleles in the gene pool. And here we again should note that the sum of all the probabilities for all the allelic frequencies sums to be negative. That is, here it is 0.55. If you add this to 0.45, so it will be equal to 1. So this is how we calculate the allelic and the genotypic frequencies in a population for a single locus with two alleles. Okay. Now let us see, this will also follow the properties of a random variable as shown in the this random variable. Okay. Now we will move on to three alleles. What if there are, say for example, three alleles in the population? Then how the things will change? Okay. So up till now we have done one of the example for this beta lactoglobulin. Okay, and whereby we have found that by simply by counting the number of genotypes available in a population, we were able to calculate the genotypic frequencies as well as the allelic frequencies in the population. Right. Now we will try to understand that if a trait is governed by three alleles, then what will be the allelic and genotypic frequencies in the population. Okay. So the genetic structure of a population for a trait with three alleles under various models of modes of inheritance have been given below with the help of illustration and example. So we will take up here this one example of ABO blood group system. I will just reduce this to 140. Let us see whether yes. So these are the you know this ABO blood group system. Okay. So group A is there, group B is there, AB group is there, and group O is there. So these are the different antibodies, and the based on the antibodies and the antigens present in the this red blood cells and plasma. Okay, we define the typing of the blood group, and this is the major blood group typing in case of humans. Okay. So now in this illustration, I will try to understand that how the allelic and the genotypic frequencies in the ABO blood group system in humans are there. Okay. So the this particularly ABO this blood group system was discovered by Carl Landsteiner in 1901, and he received the Nobel Prize in Physiology and Medicine in 1930 for this discovery. So the ABO blood group system is used to denote the presence of one, both, or neither of the A and B antigen on erythrocytes. Okay. So the ABO blood type is controlled by single gene. Okay. This is one of the identification in genetic background, that is, it is ABO blood type is governed by single gene, and that is called as ABO gene, with three type of alleles inferred from classical genetics. If I infer from classical genetics, they used to denote these as I, small I, IA, and IB. So now instead of this I or IA, IB, for ease of understanding, I will be using A, B, and O. That is, small I is for O, this IA for A, and this IB will be for the B, so that in statistical denomination you will be able to understand. Now, the mode of inheritance is such that A is codominant over B but is dominant over A, O. B is codominant over A but dominant over O, and O is recessive to both A and B. So here comes your knowledge of the genetics part, that until unless for a trait, if you don't know the mode of inheritance, so you will not be able to deduce or enumerate or estimate the allelic and the genotypic frequencies in the population. And it is applicable to humans, other primates such as apes and old world monkeys. And here the inheritance is both autosomal codominant and as well as recessive. Now, what will be the phenotypes? So individual with AA and AO genotypes will have A blood group. This BB and BO genotype will have B blood group. Individuals with AB genotype will be having the AB blood group, and those with the O genotype, OO genotype will be having O blood group. So in a population of 900 individuals were screened genetically for the presence of ABO, and following genotypes were mapped to different individuals in the sample population. Okay. Now what we have to do is that we have to calculate the gene and genotypic frequencies of this sample from the population, right? So in the sample of 900 individuals, it was found that the 150 were having AA genotype, then 90 were having AO genotype, 120 were having BB genotype, 180 were having BO genotype, and this AB was with the 300 people, and OO genotype was with the this 60 people, right? So now we have to find out the allelic as well as the genotypic frequency in this case. Now, in the earlier example, we were having A and B only alleles, but here we will be having three alleles, that is the A, B, and O. So how we will be doing this thing? So instead of the two dummy variables, we will be having three dummy variables. So one will be A, other will be B, and the third will be O. Okay. So again the same thing, because it is a diploid organism, this A can take different values 0, 1 or 2. This B can have different values 0, 1 and 2, and this O can have different values 0, 1 and 2. Say for example, if this have 2, 1 or 0, now this particularly, because this is 2, so both B and O will be 0. Similarly, if this is 1, so what can happen is that it can be 0, it can be 1. Okay. So I am working as for the genotypes of similar type actually. Okay. So this will be your AA, this will be your AO, both will be A blood group. Okay. Then if I consider this as BB, then BO. So this BB will be 2, 0. This BO will be 0, 1 and 1. And then will be your AB. So for AB it will be 1, 1, 0. And then it will be OO, O blood group. So it will be 0, 0 and 2. So now with these 6 type of genotypes, all the dummy variables have been assigned. Okay. Now A can have either of the 0, 1 or 2, B can have either 0, 1 or 2, or O can have 0, 1 or 2. In such a way that A plus B plus O will always be equal to 2, mathematical. If we see this thing as mathematical. So similarly, now we are having the number of genotypes distribution in the population. So we will be multiplying this number with these dummy variables for A, B and O differently. So first we will be calculating for this A. So it will be this 2 into multiply 150. So it will be 300. So here it will be 1 into 1990. Here it is 0. So it becomes 0. Here it is 0. So it becomes 0. Here it is 1. So it becomes 300. And here it is 0. So it becomes 0. Okay. So if you total them up, so it comes out to be 690. For B particular allele, we are having this 0, so it is 0, 0, 0. For 2, 2 into 120 is 240, 1 into 180 is 180, 1 into this 300 is 300, and because this here it is 0, so it will be 0, and if you sum them up, so it will be 720. Now for O blood group, similarly, we have to multiply these random, dummy variables into the number of individuals. So, or the genotype, number of genotype, right? So, when we will be multiplying, we have found that the number of individuals with O allele are 390 in the population, right? So similar way, if we add all these, you will see that it will be the twice the n dot dot, that is the, it will be equal to 1800. Okay, so this if I this gene pool, the total number of alleles will be equal to twice of the n dot dot. Okay, so here we have seen that A plus B plus O will always be equal to 2 because these are a diploid organism and only 2 alleles can occur at a time. Okay. So if I go with the same thing, okay, so the different genotypes can easily be calculated using their relative proportion in the genotype. So every genotype number of individuals has to be divided by total number of genotypes, and this is how you will get all the genotypic frequencies, and when you add all these genotypic frequencies, so you will get one. So the genotypic frequency for AA genotype is 0.167. For this it is 10, it is 133, 0.200, 0.330 and 0.067. And when you will be adding all these up, so you will get the equal to 1. Now we have to find out the allelic frequency. For allelic frequency, I told either you multiply that by 2 or you add all the number of alleles available in the population. So it is equal to 1800. And when you have to calculate this allelic frequency, you have to divide the proportion of that particular allele divided by total alleles in the gene pool. So here we will be dividing this 690 with 1800. So you will get the allelic frequency as 0.383, this as 0.400 and this as 0.217. And when you will be adding these all up, okay, so you will ultimately be getting the equal to 1. So this is how we can extend for from the 2 alleles to 3 alleles. That is how we extend. Now, I am signing off now for the first session, and we will resume at 4 o'clock our next session, where we will try to understand that if there are k alleles, that is any number of alleles, then how we are going to calculate the allelic and genotypic frequencies in a population. So thank you very much for your patience hearing, and we will soon be back after 10 minutes, 12 minutes break at 4 o'clock. Thank you very much.